What's up, scholars? Mr. Hipschman here. Just a little tutorial on this question. It's number 25 from, it's our Unit 4, but the book's Unit 6 from Giancoli on work, power, and energy. So in that book, it categorizes problems 1, 2, or 3 in terms of Roman numerals. This is a problem that's listed as a 3. Now, on its face, I think this is a tricky question because it combines what we learned about forces with what we're currently learning about both work, but also the last question, especially question E, requires that we use a work kinetic energy theorem. So it puts a lot of pieces together, but I think step by step you can work through it and really make sense of it. So let's do that together right now. So it says a 285 kilogram load is lifted 22.0 meters vertically with an acceleration A equal to 0.160 g, which is the same as saying it's 16%, 0.16, of g of 9.8. So that actually gives you a number value, even though it's all symbols. We'll come back to that. By a single cable, so it's being pulled up. Determine the tension in the cable, A. B, the net work done by the load. C, the work done by the cable on the load. D, the work done by gravity on the load. And E, the final speed of the load, assuming it started from rest. So we're going to jump right in, and as you notice, it asks about tension, which is sort of a classic indicator that it's going to be a Newton's second law question. And then D through E is more of our current unit, so we have to kind of smush some things together, which is honestly pretty good review for our exam. So I'm going to start by drawing a picture and setting up Newton's second law for A. Go ahead and try that, and then you can pause and then unpause when you're ready to see my work on that. All right, so I've taken all of this information. This is linked on Google Classroom if you need it. But take a look here. Here's how I've set it up. So I've got my picture, very basic picture of a box with mass 285 kilograms being pulled upwards. I've labeled the height, the acceleration, the initial and final speeds, and that one of the things we want to know is the tension in that. I've also listed those givens again just so they're very clear. So I'm not holding that in my brain, they're just written on paper. I don't have to think about it. And then A asks about the tension, and I mentioned before, but we know that means that we're going to need to do something with Newton's second law, so we'll label that just so it's clear. We're talking about the second law. F net is equal to ma, sort of our bread and butter equation. And then I've also gone ahead and drawn a free body diagram. Notice I've drawn the tension a little bit bigger than the weight mg. This is just the weight of our box. And the reason I've done that is because we know that it's accelerating upwards, and I've also labeled it with the acceleration a. So our next move is, of course, to take our free body diagram information and plug it in over here. We actually have a surprising amount of information in this one. Let's just start with symbols, and then we'll fill in our information as we move forward. So the net force, here it's pretty obvious. We're going to pick up to be positive, down to be negative. Typically, we want to pick our up to be in the same direction as the acceleration. It's generally going to make life easy for us to do it that way. So that means we have tension up. That's one of the net forces. It's one of the forces contributing to the overall acceleration. And then we're going to do minus mg, and that equals m. We'll just leave it as ma right now. We actually already know the acceleration. Let's rearrange this so that tension is all alone. So T equals, or let's add mg to both sides. So that would be ma plus mg. Now, I'm going to opt to get a little fancy here. So we're going to factor out the m's, and then we'll plug in the acceleration, and we'll see what we get. So T is ma plus g. Again, I've just factored or like undistributed that m out of there. And then on my next line, remember that a is 0.160 times the acceleration due to gravity, which is going to work out kind of cool here. You're going to see that in just a moment. So the tension is the mass times the acceleration, which is this number here. So I'm plugging that in. Plus, and then so that it's clear, I'm going to call this 1g. It's just g. The 1 is hiding. I've just written it down so it's more clear. So the answer, we can actually leave this in terms of g. We'll calculate a numerical value, but The answer is just 1 plus 0.16 g times the mass. So the tension is 1.16, I'll make my ones consistent, 0 g times m. I've written that in kind of a funny way. Now let's write it in a nicer, neater way. Sorry to have to erase here. So I think this is actually really helpful to write it this way. That means the tension in the cable is 1.1 times the mass times gravity. That's just 1.1 times the weight. So for context, we're going to put that off to the side. So 1.16 times the weight of the box, which makes sense. This tension, or this string, is under tension in sort of the same way that like a fishing line would be under tension if you were pulling on it. So I am going to plug my numbers in. This is one of the advantages to just using symbols until the very last moment. I don't have to plug a bunch of information. I'm just plugging in the mass and the acceleration due to gravity, mg. Now I wanted to give you some context before I reveal the final answer for the tension, just because I know some of us it's easier to work with numbers. So we just said it's 1.16 times the weight of the box. I just calculated the weight of the box to be this. It is m times g. It's 2973 newtons. So that would be the weight in newtons of the box. The tension should be bigger because we're moving upwards. It has to work hard to move it upwards. When I punched that all in my calculator, I'm rounding, but I got 3,240 newtons. So the tension in the string is 3,240 newtons. Again, I got a little bit ahead of myself, but we can do a quick gut check. Is this about 16% bigger than this? Just purely just glancing at it, yeah, it looks about right. So now that we, now that we know the a bunch of stuff, we've set everything up, let's move on to letter B. It says we want to know the net work done on the load. So that's going to be just equal to force in the parallel direction times the total displacement. So up here we're kind of lucky. The tension is acting parallel to the weight force. Everything is just in one dimension, one direction, up and down. So that means that our force is parallel, and so we'll just substitute this in. The net work is equal to MA times D, where MA is equal to F net. It's just Newton's second law. I've written it backwards, but it's just Newton's second law. So what we can do there is plug in the information that we know. So the net work is equal to M times A. Well, we know A. It's 0.16 g times the total distance. We'll just write that as d for right now. So I'm going to rearrange this just a little bit. I'm going to pull the constant out front, smush the mg's together, and just rewrite that. I apologize for running out of room here. So the net work is 0.16 mg times d. Let's plug everything in and let's get an answer. So net work is 0.160 times 285 kilograms times 9.8 meters per second squared, all times, 22 meters in height. Excellent. So I'm going to punch that in. We'll reveal the answer. So when we punch all of that information in, get rid of that. When we punch all that information in, we end up with 9,800, and we're rounding here, 30. Remember, we're working with work, so joules worth of net work done. So that means that actually energy was added to the system by that net force. It was 983 joules worth of work done or energy added. They're the same. So one of the reasons why problems like these are so challenging is that if you don't have parts A and B, when you get to C, you're going to be like totally mystified by it. But C is relatively easy if you've done everything else correct, which we have. So let's take a look. It says the work done by the cable on the load. Now, the cable, well, that was the thing providing the tension a little bit earlier. So when we set this up, we're going to use this tension as our force, which is in the parallel direction. The reason we didn't use that for part B is because the language was very specific. It says the net work done. When we look at C, it's important to look at like the nouns here. So the work done by the cable on the load. So let's try that with letter C here. So letter C is the work, and I'm going to be careful to label here, done by the cable. So that's going to be the force in the parallel direction. We're going to replace that with tension in just a moment times the displacement. So we've actually done the work to make this really easy. That's just the tension times D. Remember the tension was 1.16 times mg, which we found last time was 324, oops, that comma goes there, 40 newtons worth of force. We've got our answer, almost got our answer for free on this one. So the work done by the cable, I'm going to plug those numbers in, we'll see what we get. Okay, fantastic. So we've used the tension that we had already calculated times the distance, that is the force times distance, the work done by the cable, and we get a huge number, especially when we compare it to what we had for the net work done. And we're going to see in a moment why this makes sense. But it's 71,300 joules worth of energy of work done by the cable. Now, we're going to have a similar question for D, which is the work done by gravity on the load. So here we need to go back and think about, okay, so work is being done by gravity, but it's being done, the force is in a negative direction. You might see the word anti-parallel thrown around. What that means is the tension is parallel to the motion. We're moving this thing, let me move it right there. We're moving it straight up, so it is parallel to the height increase, the distance, the displacement that it occurs. However, gravity is working against that. So gravity is going to be negative work done here. And so let's work through that. So I've set up how we're going to calculate the work done by gravity. It's just the parallel force times the displacement, just like every time we calculate the work done by something. Here, the parallel force done by gravity, or acting from gravity, is negative mg. Your hint on some of these, where do these come from? Frankly, you can get right from your free body diagram. Another great reason to draw a free body diagram. So for part C, part C, we had the tension acting up. We knew that was going to be our parallel force here. That was our parallel force. When we get to part D, we look at our free body diagram, and again, we have our force mg acting down. So our parallel force for the work done by gravity is going to be negative mg. Now, I don't want to confuse folks, but if you wanted to, you could have done part B using this net force setup. We actually did that, but again, I don't want to confuse you too much, so we'll gloss over that for now. So we know all of this information. We can just go straight to plugging it in. So I had left off right here at the work done by gravity, and I plugged all the numbers in. We get negative. It's important that it's negative. This is energy being removed from the system, or gravity's trying to work against the work done by the tension. So anyway, the work done by gravity is around negative 61,400 joules. I want to give you a bigger picture view here. I want to just quickly review part B. We said net work. One other way you could have calculated net work was simply find these two works. So if we take the work done by the cable and we add that to the work done by gravity, we end up with 71,300 joules minus, because this was negative, 61,400 joules. And when we do that, well, it might be a little bit off because we did some rounding, but that's not a big deal. 61400, and we end up with 99. Yeah, it's very, very close. So 99, that's the net work done. 9,900 joules. And when we compare that, we go back. We were in that same sort of ballpark. Again, I did a little bit of rounding here, but I wanted to show you an alternate way to do B. And now we'll move on to part E, which is actually pretty easy once you've got this number here. So I'm actually just going to keep our 9,900 joules because that goes right into E. E says find the final speed of the load, assuming that it started from rest. We just talked about this. The net work done, so this is E, is equal to the change in kinetic energy. And I'm going to break this out quite a bit. The net work done, I'm going to cheat here. I'm just going to plop that number in. The net work is 9,900 joules, or what did we say, 98.3, so close enough. And that's going to be equal to the final velocity, or the initial kinetic energy, and the final kinetic energy, the final kinetic energy minus the initial. They've made it easy for us. They tell us that the initial velocity is equal to 0. And so all we have to do, we also know the mass, is solve for the final. I'm going to go ahead and do all of that, show you the answer, so we can wrap this up. All right, so I've done some algebra. I multiplied by 2 divided by m. I come over here, take the square root. So the final velocity is 2 times the net work done divided by the mass, and the answer is 8.34 meters per second. Couple things, I goofed up. I changed it. The correct unit there is kilograms for the mass, 285 kilograms. Additionally, when I was doing this on my calculator, I almost forgot not to take the square root. So please, 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 you've done all this hard work. Make sure you take the square root. Get all your credit for that one. So to review, the reason that number 25 was just so darn difficult is because you're putting a lot of pieces together and it builds on top of itself. So it's good to get back to basics. Make sure you start with a picture, you write down what you know. In this case, it was helpful to do a free body diagram and then just work through it very systematically. Don't just jump towards trying to answer each question. Thank you so much, scholars. Please do reach out with questions, and have a fantastic day.